We noted in our descriptions of atoms that different electrons have different energy levels. The electrons in the outermost shell or energy level of an atom are called valence electrons. They are the ones involved in reacting with other atoms. Whenever compounds form, they are either transferred from one atom to another or shared between the two atoms. A full shell or energy level has 8 electrons, and atoms react with other atoms to try to fill their outer shell. So an atom with 7 valence electrons, like chlorine, wants to react with an atom that has 1 valence electron to give it a complete set of 8. Sodium, Na, has 1 valence electron, so it and chlorine readily react with each other to form NaCl, also known as sodium chloride or table salt. Electrons in groups 1 and 2, with 1 or 2 valence electrons, are usually seeking to give away their extra valence electrons. Those with 6 or 7, like the elements in groups 16 and 17, prefer to take electrons from other atoms, and those with 3, 4, or 5, like the elements in groups 13, 14, and 15, are usually content to share their valence electrons. Hydrogen and helium are much smaller and can only hold a maximum of 2 electrons before all of the energy levels are full. So instead of reacting to get up or down to 8, they react to get to 2 valence electrons. Helium has 2 valence electrons in its natural state, so it already has a full outer shell and doesn't want to react with anything. The other elements in group 18 all have 8 valence electrons, which also gives them a full outer shell. Since they already have full outer shells without reacting, they don't have to form chemical bonds. These elements in group 18 are called noble gases, and they did not take part in chemical reactions, so they do not form compounds. Therefore, they are the most stable elements on the periodic table. Since there is more than one version of each element, different isotopes, a periodic table cannot tell you specifically every single kind of atom. However, by giving you multiple values and using weighted averages, you can still get a pretty good idea. The atomic number, which will be at the top of an element's box, will tell you the number of protons in an atom of that element, and since the number of electrons equals the number of protons, it also gives you the number of electrons. To find the number of neutrons, you have to use either the atomic mass or mass number. The mass number is the number of protons and neutrons in one atom. So to find the number of neutrons, you would subtract the number of protons from the mass number. However, because of the issue caused by isotopes, most periodic tables will only give you atomic mass, not mass numbers. Since isotopes have a different number of neutrons, every isotope of an element will have a different mass number, which would make the periodic table very cluttered and confusing. Instead, periodic tables usually only give one number which averages the mass numbers of that element's isotopes, taking into account the abundance of the isotope while doing so. In other words, atomic mass is a weighted average of the mass numbers of the varying isotopes of an element. Let's look at the simplest atom, hydrogen, as an example to clarify this concept. Some hydrogen atoms have a mass number of 1, and some others have a mass number of 2. Hydrogen atoms with a mass number of 1 are much more common than those with a mass number of 2. Its atomic mass takes this into account. Let's say that hydrogen 1 makes up 98% of all the hydrogen atoms in the universe, and hydrogen 2 atoms only account for 2%. If you were going to find the average mass of hydrogen atoms, you could measure the mass of every hydrogen atom in the universe, add them together, and then divide by the total number of atoms. This would be a nearly impossible process, though. But if you could do it, the average would be closer to 1 than to 2, because of how many more hydrogen 1 atoms there are than hydrogen 2 atoms. The atomic mass, therefore, would be closer to 1 than 2. There is a much easier way to do this than to count and measure every atom in the universe, though. If we know that 98% of the atoms in the universe have mass of 1 and 2% have mass of 2, Then we can multiply 0.98, which is the decimal form of 98%, by 1, and record our answer. Then we can multiply 0.02, which is the decimal form of 2%, by 2, and add our answers together. The final answer should be just over but still close to 1. The final answer would be the weighted average mass number of the isotopes of that atom, or the atomic mass. The formula below summarizes the process. It's percent abundance of isotope A times the mass number of isotope A plus the percent abundance of isotope B plus the mass number of isotope B, and so on for isotope C, D, E, however many they have. And the sum of all those is the atomic mass. Another way to think about it would be to look at the average age of your classmates. Most 6th graders are 11 or 12 years old. But is the average age of your class going to be 11.5? It probably isn't, because there may be more 11-year-olds than 12-year-olds, or vice versa. You would have to find the average in a way that accounts for how many of each age student there is, or in other words, how abundant each age student is. This is called a weighted average. To find the real answer, you could add the ages of every student and then divide by the total number of students. Or you can find the percent abundance of 11-year-olds and 12-year-olds and calculate the weighted average. If you have a small class, the first option would be easier. But if you have a big class, it would be easier to use the second approach. In the case of atomic mass, the second approach is always easier. We're going to do one practice problem together. Chlorine has two isotopes, chlorine-35 and chlorine-37. Chlorine-35 accounts for 76% of all the chlorine in nature, and chlorine-37 accounts for the other 24%. To find the atomic mass, we will multiply the mass number of the first isotope, its abundance, so 35 times 0.76, and then the mass number of the second isotope by its abundance, so 37 times 0.24. Our two answers should be 26.6 and 8.88 respectively. When we add these two together, 26.6 plus 8.88, we get 35.48, which is the atomic mass of chlorine. If you look at a periodic table, specifically the atomic numbers, you'll immediately notice a pattern. You may also notice a similar pattern emerge for atomic mass. A periodic table is a chart that organizes the elements according to their physical and chemical properties. So these patterns emerge for almost any property that you look at, though the different properties don't all follow the same pattern. As a result of these patterns, an element's position on the table relative to those around it make it possible to predict its properties, such as atomic mass, melting temperature, electronegativity, or polarity. Some periodic tables are even colored and labeled to focus on some of these properties and help reveal the patterns. As a whole, the periodic table is laid out in groups and periods. Groups are the vertical columns, and periods are the horizontal rows. One of the most important properties of each element revealed by their position on the chart is the number of valence electrons. This is especially important in predicting how reactive a particular element will be and in which reactions it will take part. The number of valence electrons increases as you move from left to right. So elements on the left are more likely to lose them during a chemical reaction and become positively charged, while elements on the right are more likely to gain extra ones and become negatively charged. Groups 1 to 13 tend to lose their valence electrons during reactions and become positive. Groups 14 tend to share its electrons, and groups 15 and 17 tend to gain extra valence electrons and become negative. Elements in group 18, because of the number of valence electrons that they have, do not take part in chemical reactions. Those are the noble gases. To tell how many valence electrons each element has, Simply look at the group number. All the elements of group 1 have 1 valence electron, group 2 has 2, group 13 has 3, group 14 is 4, group 15 is 5, group 16 is 6, group 17 is 7, and group 18 is 8, or a full set. If you notice, I skipped a big section of the elements, groups 3 through 12. These are the transition metals, and they all have either 2 or 3 valence electrons, but they don't adhere to the pattern as well as the other elements. Different periodic tables will give you different information about each element, but they pretty much all have at least the atomic number, atomic mass, and element symbol for each element. The atomic number will be at the top, the atomic mass will usually be at the bottom, and if you're not sure, it'll be the one with numbers to the right of the decimal, and the element symbol will be in the middle. The element symbol will be one capital letter or one capital letter followed by a lowercase letter. These symbols are an abbreviation of the element's name. Some of them may not make sense at first, but we have to recognize that some elements have been known for hundreds or thousands of years, so their names may root in older languages. Many of the element symbols are based on these older names, usually Latin. Iron symbol is Fe, because the Latin word for iron was ferrum. Similarly, gold symbol is Au, because their word for gold was aurum. Another little trick when looking at elements' names is to look at the last few letters. If they end in IUM or UM, then the element is a metal. Elements like iron, gold, or nickel, which seem to break this rule, only do so because we're using the English word for the elements. The original name on which their element symbols are based end in UM. We don't have to memorize the periodic table, but we must be able to read it and recognize the different types of information in it and know how it organizes the elements.